Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, good morning. Let me add my welcome to MSR Cambridge. Now, we're sort of 40 or 50 years into the digital revolution, and it's been driven by one extraordinary fact. The fact that you can fit, the number of transistors that you can fit onto a piece of silicon doubles about every couple of years. That's called Moore's law, and that is at the heart of the digital revolution. And it's fundamentally different from any other technology in human history because it grows exponentially. Everything else grows linearly. It goes 100, 200, 300, 400. This technology grows exponentially, 100, 200, 400, 800, and so on. That makes it fundamentally very different. Because it's not just the IT industry that's benefited from exponential growth, of course. It's touched pretty much every aspect of our lives. And some aspects have been utterly transformed. Other aspects, for example, education, I think are on the brink of a major transformation. Well, today we're seeing, for the second time in human history, another kind of exponential growth. It's an exponential growth in the quantity of data in the world. It seems to be doubling about every 2 or 3 years, and it's interesting because data contains information, and that information has value to businesses, to society. So computing is undergoing a transformation. It's becoming data-driven, and there's a lot of hype and discussion around big data and so on. I think it's very fundamental, and the reason I think it's fundamental is because it's an exponential growth, and that's qualitatively very different from any other kind of behavior. So what can you do if you've got data? Well, there are lots of things you could do. A good place to start is just to visualize the data. Here's some data from our computational sciences group. A good place to start gives you a flavor for the data. Maybe plotting crime statistics might already give you useful information. Always a good place to start. Next thing you can do is compute statistics of the data, compute functions of the data, averages, trends, that sort of thing. Now you're starting to get more useful information out of that data. When you run out of steam with that process, you can then sort of bring up the big guns. You can turn to machine learning. And Ken mentioned an example of machine learning, which is Connect, which is, we can think of this as a prediction engine. We think of this as a box which takes, in this case, a depth image as input, and its output are the labels of the body parts, left hand, right elbow, and so on. And we show, in the case of Connect, 1 million examples of pairs of inputs and outputs. So we tune all the parameters up in the middle, and it becomes very good at taking a new depth image and predicting the body parts. And of course, there are thousands and thousands of applications now of machine learning, and in particular of these prediction engines, to predict all kinds of things. But if you really want to go the whole hog, if you really want to bring out the heavy artillery, then you go to probabilistic modeling. And that's really the subject of this talk. So it's sort of machine learning on steroids, if you like. Now, along with the data revolution, computing is undergoing a major transformation in another sense as well. So again, for the last 50 years, we've thought of computing as based on logic. It's based on Boolean algebra. Okay? Everything is binary. It's 0 or 1. It's deterministic. It has a precise value. And computers work because they act in this very precise and predictable way. All that changes when we move to the world of data, because everything in the data world has uncertainty. So if I want to know what movie should I recommend to the user, I may know something about their preferences, but I can't be certain which movie they're going to like the best. So there's uncertainty. Which word did the user write? I mean, my handwriting is so bad, even I have trouble reading it. Right? There's a huge amount of uncertainty. Speech recognition, notoriously difficult technical challenge, often a lot of ambiguity in what did somebody say, particularly if it's in a noisy environment. Which web page is the user trying to find? Which link are they going to click on? What product do they want to buy? Which gesture is the user making? Uncertainty is everywhere. So uncertainty is very fundamental to this next phase, this data-driven phase of the computing revolution. So we need to be very clear about the way we manage uncertainty. In particular, we need a foundation, a principal foundation, a mathematical calculus for dealing with uncertainty. Now, luckily, this was all figured out 250 years ago by the Reverend Thomas Bayes, and particularly the French mathematician Laplace, and they developed a branch of mathematics called probability theory. And probability theory is the foundation. It's mathematically provable as being the unique, consistent calculus of uncertainty. If you want to describe uncertainty with numbers, then either using probability theory or something that's equivalent to it, or what you're doing is inconsistent or suboptimal. So we use probability theory. Now, this is not just a little tweak. I think, oh yeah, add a bit of probability theory and off we go. This is very, very fundamental and very different. And I'm just going to use this to illustrate why it's different. Think about the numbers 1, 2, 3, 4. Okay? I can put them in order such that 2 is bigger than 1, 3 is bigger than 2, 4 is bigger than 3. But they're what we call transitive. I can't put them in a circle so that each one is bigger than the previous one, obviously. Okay? That changes when you go to random numbers. So just think of these dice. Imagine these are unbiased dice. They're equally likely to land on any one of their 6 sides, but they've got unusual choices of numbers on them. And these special choices of numbers mean they are now non-transitive. So if I hadn't told you this, I could win money off you in the following way. I play a game. I show you these dice. I convince you that they're not loaded, that they're equally likely to land on any of these sides. And you can inspect them. You can look at all the numbers, and then you can pick one of them. Let's say you pick the red die. Then I'll pick the yellow die, and we'll roll them, and whoever gets the higher number wins. And we'll play an odd number of games, say 9 or 15 or 21 or something. And whoever gets the higher number of, whoever wins the biggest number of times wins the bet. Well, the yellow die will beat the red die 2/3 of the time. So if we play, say, 9, 11 rolls, I'm almost sure to win money off you. Okay, you get a bit fed up losing money, so you go for the yellow die. That's great, I'll pick the purple die. I'm going to win 2/3 of the time. Whichever one you pick, I can pick a number that's going to beat it 2/3 of the time. Okay? Absolutely bizarre and weird. And if you don't believe me, we're going to be giving out little tins of these non-transitive dice. So for your friends who didn't come to Microsoft Research and who weren't carefully selected to participate in today's event, you can take them to the cleaners. The only thing is we're only handing those out at the very end of the event, so you do have to stay for the last talk. Okay, so that's sort of probability theory in the abstract, and I want to show you a little demonstration of how we can use probability theory in a real application. So I'm just going to switch to this demonstration. This is going to learn about my movie preferences and make recommendations. This is actually a toy demonstration put together just for talks like this, but the technology that drives this is used in real applications. It's a toy demonstration in the sense that we've deliberately stripped out all information about the type of movie. In practice, you know that it's a romantic comedy, you know the director, you know the actors, you know the length, you have lots of features. We're going to pretend we don't know those. You also may know something about the user. You may know their gender, their age, and so on, and that may correlate with movie preferences. Again, we're going to ignore that. What we do have, though, is a large body of data from Netflix, which really just says that user number 53 liked movie number 5 and didn't like movie 7. Okay? We don't know anything about the users or the movies, just which people liked which movies. The system's already been trained on hundreds of thousands of those preferences, but it knows nothing about me. So it's going to start to learn about my movie preferences. So it might just, to start with, you might just recommend popular movies, but let's say I watch one of these movies. When I found the mouse, there it is. Let's say I watch this movie and I like the movie. What I'll do is drag it across to the right-hand side just to tell the system that I like that movie. Okay, what it's doing is it's reordering all the other movies that I haven't seen according to the probability that it thinks I will like the movie. So if the movie is down the right-hand side, if the movie is down the right-hand side of the white region, it's very sure that I will like that movie. If it's down in this white region, it's very sure I won't like the movie, and in the middle it's 50-50. Now, the only thing it knows about me is that I liked Pretty Woman. It doesn't know anything else at all. So it hasn't got much to go on. And if you notice, most of the movies are clustered in the middle. There's a lot of white space here, a lot of white space here. Most of the movies are in the middle. It's pretty uncertain about whether I'm going to like those movies or not. So obviously what we need to do is to give it a little bit more data. So what I'm going to do is find another movie, and let's say I watch this movie, and let's say I don't like this movie, so I'll drag it across to the red region. You see what's happening? Even after 2 data points, they're starting to spread out. The movies are moving towards the right-hand region where it's more confident that I like it, or the left-hand region where it's more confident that I won't like it. So what we're seeing is a reduction in uncertainty as a result of seeing data. Now, that's the modern version of machine learning. Right? We used to think of machine learning as tuning parameters to predict outputs given inputs. But in this broader view of machine learning, we think of the computer, the machine, the computational engine, learning by virtue of its uncertainty reducing as it sees new data. Let me just give you or give the system a couple more examples. Let's pick a couple more movies. Let's say I like this one. And let's say I dislike this one. Well, you notice after just 4 examples, is getting pretty confident. There's a bunch of movies down here. It's pretty confident I'm going to like these, pretty confident I'm going to dislike these. There's now a lot of white space in the middle. So those probabilities have moved towards 0 and 1. It's much less uncertain. It's learned from those 4 data points. And there's a few in the middle that it's just not sure about. And I just can't resist making just one more little technical point, because I think this is rather nice. Supposing I take a movie here, it's very confident that I'm going to like this movie. So let me drag it across and say, yes, actually I do like that movie. Watch what happens when I let go of the mouse button. Okay, very little change. The reason was it was sure I was going to like the movie. When I said, yes, I do like the movie, it was very unsurprising. So there's very little information in that data. If I do a similar thing, if I take this movie and say, no, actually, in fact, although it was very confident I was going to like that movie, in fact, I didn't like the movie. Let's see what happens. Let me do that. Okay. It's a nice demo because you can unrate movies as well. Let me rate it this time as one that I didn't like. Okay, you see a huge change. Okay, the reason it's very surprising to the system is very confident that I was going to like the movie and I said I didn't. So there's a lot more information in the data. And in fact, Claude Shannon invented the field of information theory in a classical paper. He posed the 3 main challenges of the field of information theory, and he solved 2 of them all in one paper. It's quite a landmark paper. And he defined information mathematically as the degree of surprise. So there's a key difference here between data and information. Every one of those ratings had a single bit of data, but some of them carried a lot of information because they had a lot of degree of surprise, and others carried very little information. So we'll come back to that point later. So that was just a simple demo, just to illustrate the idea of learning in the face of uncertainty. But actually, the engine that powers this, a system called Matchbox, is also used at the heart of recommendation engines, and in particular the recommendation engine on Xbox Live, which is serving 100 million recommendations a day, and you can see a demonstration of that outside during the breaks. Of course, I'm a scientist, and I can't resist going into just a little bit of technical detail about how this works, okay? But I promise you no mathematics. I'm just going to choose a very, very simple example and illustrate it with pictures, just to give you a little flavor of what's sort of going on under the hood, as it were. So I'm going to choose the following problem. The problem is ranking people in the face of uncertainty. So imagine we're all members of a chess club, and we play games of chess against each other. We want to know who's the best chess player, who's the second best, and so on. And the problem is we have uncertainty. Let's say you're a stronger player than me. That means most of the time you're going to win. But sometimes I'll beat you even though I'm a weaker player. If there's a big difference in strengths, then very rarely will the weak player win. If we're very closely matched, quite often the weaker player will win. But the outcome of any particular game is uncertain. So there's a standard technique for dealing with this. It's called ELO, named after its inventor. It's used in many, many games throughout the world. If you're a chess player, you'll have a rating. Your rating will be determined by the ELO algorithm. Okay, it's a classical, non-probabilistic algorithm. It assigns a unique number to every person. When you win or lose, that number goes up or down. So a single number for each player. And there are lots of limitations to ELO. It doesn't apply if there are more than 2 players. It doesn't apply if there are team games. Well, researchers in the lab here, back in 2005, produced what we call a Bayesian system, a probabilistic solution to the problem of ranking in the face of uncertainty. It's called TrueSkill. And TrueSkill was launched as part of the Xbox Live platform, and it's used today there are something like 50 million users of Xbox Live. There are about 150 competitive game titles on Xbox Live, and all of the outcomes from all of those titles, the outcome of every single game played on every one of those titles today is ranked using TrueSkill. And it's very important because TrueSkill is used to do matchmaking. So you say, hey, I want a game of Halo or something. In the next few seconds, the server is going to try and match you up with other people around the world who have a similar skill level. So that skill level is very important to the service. So how does this all work? Okay, well, I'm going to draw pictures, but these are actually the pictures that we as researchers will draw on the whiteboard. They're called factor graphs, and they're pictures that we draw when we're building new models and trying to solve new applications. So here's how it works. Imagine 2 people playing a particular game, maybe a game of chess or a game of something on Xbox, for example. instead of giving every player a particular skill level, 123, we're going to give them a probability distribution. We use a thing called a Gaussian, it's that bell-shaped curve. It has a mean, a middle, but it has a width, and that width is the uncertainty. So your skill, instead of being 120, might be 120 plus or minus 10, might be 105 plus or minus 20. Okay? There's a mean and there's an uncertainty associated with it. Likewise for the other player, the second player might have a different skill level and perhaps less uncertainty because we've seen more data from them in the past. Now what we do is we consider the particular game on which they're going to play, and we allow for the fact the weaker player can win by assuming they have a performance on that particular game, which is a noisy version of their skill. It's as if my skill is my average performance, sometimes a bit better, sometimes a little bit worse. And again, that's another one of these Gaussian distributions. I think of it adding a little bit of noise for this particular game. Then finally, we simply say whichever player has the higher performance is the winner. That's our little model of the situation. So we first of all build our model, then we go out and we collect data, and we illustrate that by shading in the node. So this node is something we've observed. We've observed that player 1 was the winner on this game. So this node is no longer an uncertain quantity. We know its value. Then what we do, the computational process we do, is we have to figure out what does that imply for the skills. So when we observed that I liked a particular movie, we updated the probabilities for the other movies. So here we observe that player 1 is the winner, and that's somehow going to increase our estimate of player 1's skill and decrease our estimate of player 2's skill, but also the uncertainty in both will reduce a little bit. That computational problem we call inference, that's where all the computational grunt is, and it can be expressed mathematically in a very beautiful way in terms of messages being passed along this graph. And the reason that those messages are important is twofold. First of all, because it's computationally efficient. We can spread this across many processors by having different processors work asynchronously on different messages on different part of the graph. So it scales very well. The other beautiful thing about this is it becomes very modular. These elements of the graph become things that we can plug together. I'll come back to that in a moment. So what you see here then is that as a result of those messages, in this case player 2 is the winner, their skill shifts to the right and it becomes a bit narrower. And player 1 was the loser, the distribution shifts to the left, but again it becomes a bit narrow because we're a bit less uncertain about their skill. Okay, let's compare old-fashioned ELO with true skill on some real data, and this is data taken from Halo. And this involves thousands of players, but let's just look at 2 of the players. This is a graph of the estimate of their skill level versus the number of games they've played. And notice the axis here, 100, 200, 300, a lot of games. Okay. This is what we get if we analyze that data using ELO. We see that everybody starts off with skill at 0, and we see that as they play games, their skill evolves. Okay, this is our estimate of their skill evolving through time. Let's analyze exactly the same data using true skill. We get a dramatically different result. This converges in terms of how much data we have to collect or how many games they have to play, more than an order of magnitude faster. So instead of having to wait for 100 games, even just after a few games, we're getting quite close to convergence. We're getting much better estimates of their skill. The reason has to do with uncertainty. I'm going to just take a moment to explain this, because this is just an illustration of the power of uncertainty. If I can pick you as an example, let's say we're chess players. Let's say I'm the stronger player, you're the weaker player. So in ELO, I'm 130, you're 120, but let's say today you're the winner. Well, the ELO algorithm would reduce my 130 a little bit to 129, it would increase your 120 to 121, and we go off and we play another game. It makes these small changes, because that's all it can do. Right? It's not able to make big changes in one step. That's sort of optimal if you don't have uncertainty. But now suppose I'm a very experienced player. I've been in the club a very long time. I'm 130, in true skill, I'm 130 plus or minus 1. Right? Very narrow distribution because the system is very sure about my skill level. You're quite new to the club. You're 120 plus or minus 20, right? Much more uncertainty. Now you're the winner. Well, intuitively you can see what's going to happen. If I'm 130 plus or minus 1 and you beat me, you must be 129 at least. So in one step, true skill will move your skill from 120 to 129. It will make a very big jump in one step because it has the uncertainties in these distributions. Now, we don't have to code that intuition. The beauty is we just write down the laws of probability and run computational inference, and it does the right thing automatically. Okay, that intuition just happens correctly and automatically. There's something else which is very important, very nice about this. It comes back to that modularity. That's true skill, equivalent to ELO, but I said that ELO had these limitations it doesn't handle multiple players. Well, we can handle multiple players very easily. We just extend the graph. That's the graph for 3 players. It's trivial to extend the graph to this more complex situation. Likewise with teams. Here's 2 teams, each consisting of 2 players. We model this just by drawing the corresponding graph, and when we run inference, the correct thing will happen. So far, I've assumed that the person's skill is constant, and what's happening is, as they play more games, we're learning more about their skill. But of course, their skill itself is probably going to change through time. If you play 100 games of Halo, you're probably better at Halo at the end than you are at the beginning. So we can allow for that. We can allow their skill to evolve through time. The player's skill at the new time depends upon the player's skill at the previous time, but it can evolve a little bit. And again, we can just model that by drawing the graph. So one of the biggest projects we have, well, probably the biggest project we have in the lab in the field of machine learning is called Infer.net. And Infer.net is a very ambitious project to deliver what we call probabilistic programming. So the idea is that for 50 years we've been programming computers using computer languages that treat variables as certain quantities, like deterministic quantities. So if x is a Boolean variable, it's either 0 or it's 1, or it may be undefined, but it's either 0 or 1 if it has a state. But now we want to deal with uncertain quantities. So x now can be what we call a Bernoulli variable. It's maybe 0 with probability 30% and 1 with probability 70%. Okay, it's now a random variable. Now again, if you think this is just a little tweak, let me just point the following out to you. Think of a standard piece of code. We have a test. If x is 0, do this piece of code, else do that piece of code. What happens is you grind through, you test the value of x, and either you do the first piece or you do the second piece, depending on the value of x at the time. Supposing x is now a Bernoulli variable. It's 0 with probability 30% and 1 with probability 70%. You don't know which. You have to execute both pieces of code. Because it could be 0, it could be 1. You don't know. You have to execute both pieces of code. And later on you might find out other information that informs the value of x. So it's very fundamental. It's very different from traditional programming. So Infer.net allows us to code up things like the movie recommender or TrueSkill or many other examples by taking that graph and expressing it as a very compact piece of programming language. So the original TrueSkill was built before Infer.net, and it took a very smart, very competent developer, researcher, about 6 months to code this up. We can put this together in a couple of hours because we can express that graph using literally 20 or so lines of code. Infer.net is then a compiler. It takes that model, as we call it, that description of the probabilistic graph, and it generates highly efficient, bespoke software that uses message passing to run inference efficiently at scale. And that's expressed in C#. That's then compiled to machine code using, again, a standard compiler. And if you want to extend the model to teams, to multiple players, and so on, you just simply change the code that describes the graph and then recompile. So it's a very, very flexible system. So probabilistic programming has actually become quite a hot topic. Earlier this year, DARPA, which is the US Defense Advanced Research Projects Agency, sort of a funding agency in the US, launched a $50 million program for academics in the US to stimulate interest in probabilistic programming. There's a lot of work being done in this field, but as far as I know, Infer.net is the only system that focuses on doing this at scale. It's the only industrial strength system that I'm currently aware of. I'm going to finish with one final comment, and it's about this phrase big data, because we hear the phrase big data. You've learned something interesting about data from that movie recommender. You've learned about the difference between data and information. So I just want to comment on big data. So when people talk about big data, we usually think they mean data that you've got so much data that storing it is a headache, moving it from one place to another is a headache, computing with it is a headache. All right? There's just so much of it. Well, let's just think about the size of a data set and what we mean by the size of a data set, because the size of a data set has 2 quite different meanings. There's the computational size, meaning how many bits are there, and there's the statistical size, which means how much information does it contain. And these are different things. I'm just going to show you 2 corner cases, sort of 2 extremes, just to sort of illustrate the point. So the first example is a data set which is computationally tiny but statistically large. So let's imagine we've got the block of material, we apply a voltage to it and measure the current, and we get some data, we get 7 data points. And our goal, let's say, is to predict the current for some new value of voltage. Well, our friendly local physicist has very kindly told us about something called Ohm's law, and apparently this has a linear relationship, so we're off to a really good start. So we can now use our favourite technique to fit a straight line, or in this lab, we would fit a probability distribution of possible straight lines. Okay, because that's how we do things in this lab. And that allows us to make a prediction, and again, we would have a prediction with uncertainty. Let's think about this. Two points define a straight line. 7 slightly noisy points define a straight line pretty well. So although there's some uncertainty in that straight line, there's not very much uncertainty. So our predictions are very precise. They're very tightly grouped. Now, that's a data set which is 7 pairs of floating point numbers. So computationally, it's a trivial data set. But statistically, that is big data. That's a large data set. By that I mean, if I give you another 1,000,000 measurements of voltage and current, your uncertainty will reduce, but not by much. It's already pretty small. I mean, after 1,000,000 data points, it's sort of getting close to 0, but it's already very small. So that data set is already a large data set statistically. And then just to sort of give you the other corner case, let's think of an example of a data set which is computationally large but statistically small. It's the problem of recognizing objects. Let's consider images of objects, buses and cars and planes and that sort of thing. Each image might have millions of pixels, and I might give you millions of examples of each. I'm going to give you millions of examples of aeroplanes, millions of examples of bicycles. Right? Each image contains a bicycle or an aeroplane. That's starting to be a computationally large data set. Millions of images containing millions of pixels, a lot of data. Is it statistically large? Well, let's think about this. What is an aeroplane? Well, that aeroplane could be in different positions, horizontally and vertically in the image. It could be at different orientations in 3D space. It could be at different distances from the camera, which would make it different sizes in that image. It could be painted different colors. It could be illuminated with different lighting. Parts of it could be occluded. Other objects could be occluding the part of the aeroplane, and so on. They're all pictures of the aeroplane. In fact, the number of possible images that I could display, which we would all agree constitute a picture of an aeroplane, is vast, vast compared to the number of atoms in the universe. Now, the number of atoms is tiny compared to the number of possible images of aeroplanes. So if I give you 1,000,000 pictures of aeroplanes, that is incredibly sparse within the space of possible images of aeroplanes. It's the opposite of the left-hand side. It doesn't fill that space and constrain it, far from it. It's very sparse. So that's statistically small and computationally large. I should just add, in fairness to my colleagues from the computer vision group, because they'd be livid if they were sat in the audience at this point, we don't naively treat an image of an aeroplane as just some long vector and feed it into a classifier. We have sophisticated computer vision techniques that recognize that it's an image that pixels nearby and so on. So actually you can build good object recognizers of things like aeroplanes using far less than 1,000,000 images, but I just choose that as an illustration. With that, I think I will stop, but I'm happy to take questions if we have a minute or two.
We have plenty of time for questions.
Stunned silence. Don't forget to collect your dice at the end. There's a question there.
In the example of the films, many films have zero value in that, if it's a blockbuster, everybody under the sun has watched it. So you gave the example of Pretty Woman. I mean, huge numbers of people have watched it. Does your approach take into account outliers that, an arts film or a film with a much smaller run is likely to carry much more information than maybe, the blockbusters?
Right, you've hit on 2 really good points. Let me give you 2 answers, because you touch on 2 very interesting things. The first one has to do with recommendation. Let's say you've just bought a weather prediction app for your phone. The last thing you ought to be shown is 20 adverts for weather prediction apps on your phone, because you've got one. You don't want more, even though you obviously liked it, because you just bought it. You obviously like weather prediction apps. You actually only want one of them. So there's something to do with diversity here. I discover you like action-adventure. Now I'm just going to show you action-adventure for the rest of your life. You'll never get to see those nice romantic comedies and so on. So there's got to be a little bit of diversity in there as well. It's not just about... So what I'm talking about here is what we call the inference problem, working out the probability that you will like each movie. Afterwards, we have a decision step, which is generally much simpler, but is equally important, where we take those probabilities, and then we try to optimize something. In this case, we're trying to optimize maybe the number of movies that you buy, or your satisfaction with watching the movies, or whatever it is we're trying to tune. We use that uncertainty to achieve some goal, and that separately is the decision step, and that might involve showing you lots of action adventures, but occasionally putting in some other movies, some documentaries and so on, just to give you a little bit of variety. And that touches on the second point, which is what we call the exploration-exploitation trade-off. And it goes like this. I'll show you a couple of movies. They happen to be action adventures. You like them. I know that you like action adventures. I've now got a dilemma, because I think you're going to carry on buying action adventure movies off me. So if I want to make lots of money in the next 5 minutes, I'm going to show you an action adventure. But maybe it turns out you like romantic comedies as well, and I can make a whole lot more money selling you those, but I don't know that because I haven't shown you any. So I've got to do a trade-off. I've got to occasionally show you other stuff so I can carry on learning, while at the same time delivering things that you need now. So I've got to trade off delivering what you want in the short term compared to delivering what you want over the long term. And there's a trade-off, and how you make that trade-off is not part of this inference step, it's part of that decision step. It depends on what you're trying to optimize, okay, whether you're playing for the long term or playing for the short term. So that's quite fundamental. And part of the solution is to recognize that every time you take an action or you don't take an action, it's data and it's an opportunity to learn. So there's sort of information everywhere, even in the things you don't do as well. So you have to think of data as a rich source of information. And, you know, a generally good policy is don't throw data away. If you're allowed to keep the data, and you know, who knows what's in there. So you know, keeping data is good, which is one of the reasons why it's growing exponentially, of course. Yep, stop there. Okay.
Okay, right. Well, thanks, Chris. Thank you very much.